So welcome, of course, and let's be a little bit patient because people are now still joining. We will not wait very long, but let's give a few minutes to all others to join. And then we will start with the ARIADNE webinar. Good afternoon and welcome to the public webinar of the ARIADNE project. My name is Halit Krasenca. I am from Euroscom GmbH. We are based in Heidelberg in Germany, and I'm coordinator of the ARIADNE project. So today we are combining two events. One of them, as already mentioned, is the webinar about ARIADNE, about our results and everything what we achieved, or almost everything what we achieved during the last almost 3 years. And also, this is at the same time the third ARIADNE Advisory Board meeting. We are using, let's say, the opportunity to involve also the Advisory Board members in this discussion. What I would like to mention on the beginning, we are going to record this webinar. So if anyone would not like to be seen, please switch off your video. If we are going to use this material for any kind of publication, of course, we will come back to people who might appear in these videos we are going to publish in order to receive your consent, of course. In these cases, we will be able, for example, to remove the names, whatever is needed in order to protect your privacy. But I think as we are in a public webinar, it should be okay for everyone. So I think, Pooja, you can already start the recording. And maybe only one remark before starting the webinar on the presentations, so that we can handle this and maybe also some of the questions leave for later on. Regarding the agenda, as you already received, we have a very, very exciting agenda, I would say. We are trying, of course, to cover the main part of the ARIADNE project, but of course it is not easy to pack everything within 1.5 hour program we actually planned for today, plus maybe some time for the discussion. But we will try, and I think the first try will be, of course, by our technical project manager, Angeliki Alexiou from University of Piraeus. She will give first an overview presentation about the targets of the ARIADNE project, the goals, and of course, the most important, the results. And then we will have 3 presentations, let's say a little bit more concrete, regarding the D-band channel modeling, important for developing the new radio technologies. Then, of course, the second point, very topical, is RIS, the implementation of the Metasurfaces in the communications. This is also part of work we did in ARIADNE. And then in order to maintain and manage this, let's say, pretty complex system, including RIS, including the high frequencies and so on, the project put significant efforts in exploring machine learning and artificial intelligence, the usage of these, let's say, technologies and techniques to manage these demanding networks. I'm happy to welcome our advisory board members, Professor Tadao Nagatsuma from Osaka University, Professor John Vardaxoglou, I hope I pronounce it at least a bit in the right direction, from Loughborough University, and Patrick Gallinari, professor at Sorbonne University. These 3 experts, I have to say, were with us from the project start. We already have some meetings, and they are all experts in the areas, in different areas, let's say also covered by the ARIADNE project. And of course, I hope after the presentations we will have a chance to receive also feedback from our advisory board members, and also to use the opportunity to present 3 of you to our audience. At the end, of course, regarding the conclusions and end of the webinar, as I said, we planned 1.5 hour for the presentations, maybe also initial discussions, but we have time, additional half hour at least, to tackle the questions and discussion so far needed. So I wouldn't lose that much time now, and would ask Angela to present technical overview, let's say, of the ARIADNE project. That's what he did, and in particular what he achieved in terms of results. So Angela, please, now you can share your screen.
Thank you, Khalid.
Of course, yeah, I would suggest that the speakers should switch on, if they wish, of course, the cameras, so we can see them. Others as wished, but as we know, because of the performance of the networks, still we have to be careful, so maybe to switch off the videos in order to improve the quality. But I think for the time being, we are really okay. So Angela, it's your turn.
Thank you, Khalid. So what I'm going to try to do is very briefly give you an overview of the objectives and let's say the main directions and the main results so far. But I would really like to, allocate most of the time to the presentations after that, so that you get really in more detail some of the achievements. But maybe for the benefit of people who are not familiar with our work, ARIADNE idea started almost 4 years ago, and the idea was to synthesize 3 important enablers, that of beyond channel communications, RISs, and machine learning. And back then, when we started thinking about it, these concepts were not that, let's say, explored. They were relatively greenfield. Over the last 4 years, that changed dramatically, and we certainly hope that we helped a little bit in making these technologies some of the core directions for the evolution of networks to the next generation. So the idea is to benefit from the bandwidth and the features, the particularities of higher frequencies, that of sub-terahertz band, the D band, and use a new radio concept that would exploit the technology of intelligent surfaces in order to create a new radio that is able to reconfigure itself, to adapt, to tune, if you want, to the particular conditions, the challenges, the difficulties, or even also the objectives and the performance targets of next generation networks. But in adding this type of intelligence, let's say, with a major enabler like the intelligent surfaces, the idea was to also introduce as an integral part a tool that is able to manage these additional degrees of freedom, a tool that is able to optimize itself, to learn, and in that way introduce this brain as a part now of the new radio, and as you will hear later, in various, let's say, fields and objectives, including modeling, including prediction of the behavior, including the optimal use and allocation of resources. So this, let's say, triplet of ideas were introduced in a system concept that would try not only to address the additional requirements of next generation in terms of throughput, for example, in terms of latency and in terms of reliability, but also create a new system concept that would have intelligence as an inherent part. And what you see here in the picture is basically our plan in boxes, in module. So we have a number of pillars, that of using terahertz, that of introducing beyond Shannon, and also artificial intelligence, and a number of objectives that we try to achieve by means of various actions that include modeling, analytical, theoretical studies, design of baseband RF and antennas, design of algorithms, and last but not least, of course, the design of intelligence of tools that leverage machine learning ideas to come up with optimal solutions for modeling and utilization of resources. The end result of the project, the outcome is not only, of course, publications, white papers, contribution to standards, but also demonstrations. And our plan is to deliver 2 hardware and one software demonstrator. And we hope to be able to do that by this summer. And we hope that EUCNC will be an opportunity for us to demonstrate these new technologies that we are currently building and optimizing. So as in what scenarios we would like to address, it is a very large and dynamic range of scenarios that we're considering. These want to cover both the idea of terahertz as a fiber extender as a way to introduce this super high, let's say, quality over the air by means of using higher frequencies. So you see point-to-point connections are part of our scenarios, but obstructed connectivity, both for outdoor and indoor, mobility and ad hoc dynamic topology connectivity are of great interest, and we think that the combination of the 3 pillars of Ariadne would definitely play an important role in addressing these challenging and complicated usage scenarios. It is difficult to summarize what we've done so far, but I would try as a final remark to, let's say, mention the categories of studies that we've done so far. So by taking into account the particularities of the environment, for example, the fact that in these high frequencies we're talking about pencil beam forming with several problems associated with that, like blockage, misalignment, tracking, etc. We kept ourselves busy with modeling and measurements of D-band channels and the composite RIS channel. Also, we try to create an analytical framework for the study of these systems that use RISs as a means towards tunability and programmability to understand, let's say, the behavior analytically, theoretically, and also come up with designs of the basic modules like antennas, RF, baseband, transceiver architectures and algorithms, and come up with a framework for optimization that uses system level and machine learning concepts. And finally, the 3 demos that I mentioned. So with that, I would like to stop here and ask you to have a look at our website, because there you can find some papers, white papers, and also some pointers towards other activities, like, for example, our standardization activities. So members of the consortium are involved in ITUR. We have already submitted contributions towards the ITUR activities towards next generation networks. And also there is a lot of interest, a lot of momentum created around the major pillars of Ariadne in ETSI standardization body with new ISGs on RIS and on terahertz recently established. So with that, I would definitely invite you to have a look at our website for more information. And of course, we are always open to question. So Khalid, over to you. I think I didn't take that much of the time, I hope.
No, you didn't. It was very quick and indeed a very, very nice overview of the Ariadne project. So, okay, I've been just checking in the chat. So there are no questions directly to you for the time being. So therefore, I think thanks again, Angela.
Thank you.
And I would pass to Joonas Kokkoniemi from University of Oulu to update us on the results we achieved in relation to the new radio technologies D-band frequency ranges, channel modeling, and all other related interesting things. Please go ahead, Joonas.
Thank you very much. Hold on, I will still check if I can open my video as well. Okay, now I'm visible and hopefully the presentation is visible as well. So just somehow hide this. Okay, very good. Okay, welcome to this ARIADNE webinar on my behalf as well. I'm Joonas Kokkoniemi, as Ali just mentioned, and I'm here to talk about, well, the title says new radio technologies, but mostly we are focusing here on the channel characterization, what we've been doing. And, of course, there are huge numbers of results that we have produced in ARIADNE. This has been really productive project in that sense. So I will really give you an intersection of what kind of results have we been producing during the project, but I will not go through too much details because otherwise I would probably need 1 to 2 hours to go through. But let's look at the activities, what we've been doing and what we have been achieving. So obviously ARIADNE use cases, they require many different kind of approaches to the channel characterization, but okay, this goes way beyond ARIADNE, of course. When we go to higher frequencies, we need different kind of approaches to the channel characterizations. So of course, even in ARIADNE, we go through, we start from long distance backhaul links, and we go to even the near field of the RISCs and some dynamic topologies. And these all are very different kind of use cases, and they require different kind of channel models and different kind of characterizations of the system. But this channel characterization alone that I'll be focusing today, this has been a very important task in the ARIADNE project. Just to shortly recap, of course, Angela already showed you a bit of what ARIADNE is all about, but I will show it a little bit from the work package 1 point of view, where we have mostly been focusing on these channel-related issues. And then after that, I will then go through in some kind of a topical order these ARIADNE results. Of course, there's still a lot of very interesting results to come. So in that sense, I will urge you to check in on us a little bit later after July, most likely when those results go public. Just to shortly look at what the work package 1 was all about. Of course, this is not all about work package 1, but the channel characterization mostly has been. So of course, task 1.1 gave the initial directions for the ARIADNE research from the use cases and requirements point of view and the KPIs. The task 1.2, this was now really the channel measurements and modeling task, and this is where today's presentation will be very heavily leaning on. So the D1.2 that was released in month 24, which was a little over 1 year ago. That comprises now quite a lot of the results, but some of very interesting things are still coming. So in the end of the project, after July, or the end of July, we are going to release the D1.3, that is then the performance evaluations, where we will have really a lot of cross-work package actions and measurements of the demonstrations, comparisons to the theoretical values and so forth. So there's still a lot of very interesting things to come. So of course the use cases, they cut through the point-to-point links, long distance and short distance point-to-point links, these RIS/metasurface communication scenarios in the indoor and outdoor scenarios, and of course these ad hoc connectivity cases or moving topologies. From the channel characterization point of view, tends to be that the point-to-point links we give quite a lot of information about total system alone, and then this reconfigurable intelligent service type solutions give then additional access to reconfiguring the channels themselves. So that is also where we are leaning today quite heavily on this kind of point-to-point link modeling, as well as the RIS. Or a few words on the RISs. On the RISs, we have so huge numbers of results that I will not go through them very much detail. So these point-to-point links, they are quite important from the fundamental characteristics point of view. That is, of course, very fundamental issue in the ARIADNE, and particularly in the D band, which is centered at around 140 gigahertz. And then enabling technologies, these RISs and metasurfaces are very, very important. But to somehow structure today's talk a little more, we'll first look at these line of sight links and what we've been doing there, and then the RIS links, a little bit what we have been doing there. Channel measurements are of course very important, because those really give the new knowledge and the confirmation for the models or modeling aspects from the links and so forth. So obviously we can then use them to model the actual channels rather than just propagation. And of course, these ray tracers are becoming more and more important when we go to higher frequencies. So line of sight links, these are obviously when we go to higher frequencies such as D band. These are the most important links you can find. These are the most desirable links, and these carry the most capacity out of any links. Even if you consider fancy RISs and so forth, still the pure line of sight connection is the most important. Now, according to my prediction, these long distance backhaul links will be among the first real so-called terahertz applications, even if quite controversially, usually this high frequency communication is considered to be short range. But in the high ranges, we can use something like what in the ARIADNE, in the hardware development side, we are using these cassette range style antennas that can generate huge amount of gain. We are talking about fixed links at that point, but arranging gain is rather easy if you don't need to move. So in that sense, these really long distance point-to-point links are quite important. And from that perspective, we will have some notable issues like gas attenuation and, for instance, rain attenuation, also fog attenuation and so forth. So in this presentation, let's a little bit look at what we've been doing about these. So one of the things what we did very early on in the project was develop this kind of a simplified model to predict the gas attenuation. I'm not going to go through this in much detail, but let's say that we have say a few tens of parameters in comparison to hundreds of thousands of parameters, what you would need for a full line by line model to predict the absorption loss. Now, it was also shown that it's really accurate, so this really helps to estimate the link budgets. But then, of course, when you have the gas attenuation, that's relatively straightforward. But then UPM, they were really looking at the gas attenuation from the empirical weather data point of view. They really look into the historical weather data and see what kind of average losses could we be expecting on the long distance links. So these are mostly now applied to the European locations, but of course this could be anywhere on the planet. We do the similar kind of analysis. I picked up Oulu because I'm from Oulu. So if you look at this is a little bit small, but we can extract weather data. This is from January 2018 all the way to January 2020. So if we look at this, we can see that temperature, relative humidity, pressure, and your water vapor densities are changing on average. So during the midsummer, you tend to have higher temperature and higher humidity than compared to the midwinter, for instance. So this will have a great impact on the specific attenuation, as you can expect. So even up to tens of dBs per kilometer difference. Now, of course, for the shorter the link, the less of an important this variation is. But for long distance backhaul links, for instance, we are shown in this project, but also in the previous project that these kind of even 1 kilometer links are possible. Now, depending on your location, your frequency, like in the lower figure, you have the different frequencies and the specific attenuations. You can have a great variations, but also great variations will not, let's say, some variations at least, depending on your location. Obviously, these are all European locations, but you can already see that there are certain little drier locations, like for instance Oulu, where you would, in average, have a little bit less attenuation compared to some little more humid locations. Of course, if you take this to, I don't know, closer to equator, rainforest, and so forth, there can be very great differences. So these are really interesting analysis, and you can really check more in this deliverable 1.2, where we have a huge amount of data on these. UPM also checked this rain attenuation, which is a really important open question, how to model it really accurately. They were really looking into the droplet shapes, shape speeds, and backed up with the measurements of the droplet sizes, for instance, and so forth. And they have been developing some rain attenuation models based on this, based on the shapes and so forth, theoretical and measurement-based data. Because the well-known fact is that ITUR does provide us models, or they do provide models, and those are kind of a good baseline to predict what kind of losses there are. The issue is that they have really not been validated to really high frequencies. So that is an important research topic still nowadays, how to really model when we go above 100 gigahertz, how to really, what are the real losses there? Because there are different kind of rain types and so forth. So ARIADNE has taken a step there and really provided new models that are hopefully a little bit more accurate than the ITUR models. And of course, this depends on the location and so forth. And same as the molecular absorption loss, also the rain attenuation, different kind of type of rain based on your just geographical location varies a lot. And there's also a huge number of results in the D1.2 about this rain attenuation. So I hope that you go and check that out. It's a public document, so it should be available. The RISCs now, these are one of the focal points of the ARIADNE, and we have so huge number of results about the RISCs that I really urge you to read all our deliverables about the RISCs. So we are really looking into RISCs from the not only from the channel point of view, but from the algorithm point of view, and many other points of view. Just quickly giving those in the following, but really some of the most interesting results about the RISCs are still to come, because we also have some real demonstrations about the RISCs, and those will be measured, and then we can compare those to the theoretical values. So that is really interesting to see in the near future when those demonstrations are ready, and we will start to get the data. But that is then in the D1.3 that will be published in the end of July, or most likely in the somewhere around the August. So just in case there are people who don't know what the RIS is, so this reconfigurable intelligent surfaces, the aim is to allow controlled reflections. So we do have some kind of a surface that has a controllable surface elements, either individual or then the entire surface is controlled as a surface. So we tend to have a situation where we have a base station. Let's call this a TX now base station. Then we have a base station controlled RIS somewhere in different physical location. So now the base station can control or jointly try to optimize the RIS and the TX phases in such a way that it maximizes the signal at the RX, or maximizes the RX signal at the base station. Now, there are some physical limitations when it comes to the mostly the size. For instance, here in this equation that depicts the received power of the RIS. So we have the dxdy, which is now depicting the size of the element. There are some severe limitations there when it comes to the capturing of the energy. So the RIS is really shine when you don't have the line of sight between TX and RX. But when you don't have the line of sight, especially in the higher frequencies where we have sparse channels, these RIS are really important in delivering some energy and delivering really good quality paths between the TX and RX. And in ARIADNE, these have been studied from so many different aspects that it is really difficult to summarize them all, other than just giving you a list of what we've been doing. So some of the important things have been the EM modeling of the RIS, so the surfaces themselves. In principle, there are two different types. You have the antenna array type solution where you are controlling each element separately, or then you have this metasurface type of solutions where you design the entire surface and you control the surface as a whole. So in any case, the EM modeling is quite important because the simplest possible models are not necessarily the most accurate ones. So especially CNRS has been really doing this EM modeling quite a lot, and they've been really analyzing even doing this kind of real measurement phase validations, as you can see some illustrations here. And they've been really trying to come up with some general formulas would predict the near field and far field fields into single general formula, or it's kind of general equation for RISs. But then, of course, really important part has also been to study this cascaded channel from the base station to RIS to user, because it is a bit different. Well, one possible solution can be seen here. It was derived by CNRS, where you will have the contributions from the phases of the elements and the propagation phase and so forth. But these depend quite a bit on the hardware that is utilized and what type of RISs are utilized. The near field are also really important, as I already mentioned. That CNRS, for instance, has been really focusing on the near field modeling along with the far field modeling, as I mentioned, the area that captures the energy is really important in the RISs, because that energy that is intercepted by the RIS is the whole energy that can be then redirected. So it is better that if the RISs are very large, so that they can redirect a lot of energy. But if you have a really large surface, then there's a danger that the user is in the near field of the RIS, and that is then creating a lot of complications in the maximizing the signal energy and the phases, because you have one additional degree of freedom in the near field of an array. Now, going a little bit further, we have also been developing some user tracking, not in work package 1 though, but this is also very important if the users are moving within the vicinity of the RIS, how to capture the or how to track the user and keep the link alive, because this is a rather complex system to optimize the phases. Now, ray tracers, a couple of words about those later, but they are really handy in analysis of all kinds of things, and among those RISs. And as I mentioned, we are developing prototypes and really interested to see the result of those, and what kind of how do those compare against the theoretical models. And there's quite a lot more as well, and there are now quite many deliverables full of results about RISs. So those who are interested in our results will dig through many of the deliverables. 1.2 is one, but also in work package 2 there have been very interesting results there, and then the actual prototypes have been developed in at least work package 3 and 5. Okay, the measurements, they are always important when it comes to the new frequency bands, such as the D band. So in this project, we have been doing some measurements on 140 gigahertz, and these have really produced quite a lot of data on the deep-band channels. And then we have further used this data in the fading modeling that I will come back to a little bit later. But we have also used this in some machine learning applications, for instance, using machine learning for channel prediction based on the real measurement data. Now, Aalto University has produced quite a lot of measurement data in this project. So they have done, for instance, measurements in their own campus, inside their own campus, in the campus outdoors, in the city center of Helsinki, and the residential area. And on top of this, they've also given the project some results from Helsinki Airport, some additional results from the entrance halls, and also some shopping malls. Just to recap, what are the main findings is that if you are in the indoors where you have quite a lot of objects, we will see quite a lot of paths in the channel. And when you go outdoors where you have a little bit less objects and less flat surfaces, we will have less paths at our disposal. It's clear in all these results. Now these results are snapshots. They are a single point, not aggregated across all the points. So we can see that no matter where we are, we tend to always have even good number of paths. Maybe the main challenges then come, how do you treat them, because you are always looking at the channel with some kind of gain in the real life. So you will not actually see all the paths. That is where then the channel modeling steps in later on. So Aalto was in their measurement system, they were utilizing omnidirectional RX, but they also utilized the ray tracing model and point cloud models to then complement the measurement data to further estimate the angles of arrival and in the both azimuth and elevation directions. So this is one very excellent use case of the ray tracing models already, that you can really use them to enhance the measurement data. We also did some here in Oulu, some measurements in our indoors, in the office corridor, and some in the cafeteria. So if we take a look at those, it is really the same story. So we see quite clear some clusters where the energy is coming from, quite a lot of paths. But if you really look at the aggregated data, that is when you have a lot of paths. But if you don't aggregate, then you have kind of a little bit less paths, but you always have a little bit paths. So that's a kind of good news, but it also then means that it is a challenge because they are really sparse, the channels. So it is a challenge for the channel estimation, how to find those. We know that it's there, but how do you use them? That is a good question for the research and for the algorithm development. So based on these measurements, especially the Aalto channel data, we have been looking into fading, because fading is really an interesting question. That how does it behave? How are the fading channels in the higher frequencies, or are there fading channels? So now, depending on the environment, we have found quite many different kind of distributions. The most useful ones we have found are some alpha mu and Pearson type distributions. So in this analysis, especially UPRC and Demokritos, they were looking at the shopping mall, airport, and Aalto entrance halls. And there are several distributions like Weibull, Pearson, as I mentioned, and alpha mu that fit really well to the path distributions and path energy distributions and so forth. Now, the thing is that the most important finding based on this kind of fading modeling and the path analysis is that it is dependent quite a bit on the environment. What are the exact parameters that you should be utilizing? And this is of course natural, because this also happens in the lower frequencies, that you need, if you have different environment, you need different kind of channel modeling. In the higher frequencies, the role of the hardware will be emphasized quite a bit, because the how you access the channels with always directional links. And now, depending on what type of an hardware you are utilizing, it has great impact on the number of visible paths. So by aggregating all the paths, we can pretty much tell how is the channel, but the exact behavior of the channel will depend also on your hardware. Now, ray tracing is a quite interesting tool, because channel measurements are really challenging at the higher frequencies. So ray tracing will really take off where channeling has to stop, or the measurements have to stop, because measurements are time consuming and difficult at higher frequency, because you always have the directionality and the scanning and so forth. Now, ray tracing has also become more important at higher frequencies because of the sparse channels. Because at lower frequencies, even smaller, the vast numbers of objects in the environment, they do radiate, or they not radiate, but scatter energy. Exactly the same thing happens at the higher frequencies, but because of the lower dynamic ranges, we tend not to see those scattered paths. So therefore, because the paths or the channels are sparse, also a little bit rougher ray tracing models tend to be giving much more accurate results, because the ray tracers in general, you have to be you're a little bit limited in the accuracy that you can utilize, just because of the raw computing power that you have at your exposure. So these are really nice devices, or the algorithms, because you can place an RAS in a realistic environment and see how it really works. So I have some examples here. So for instance, Nokia, they were developing an RAS, ray tracer in this project, and you can really study the signal evolution. For instance, this is downtown Helsinki. So they have a 3D map of Helsinki, and you can really just place the TXs wherever you want and put the RXs in a path and see how the signals evolve. And then on top of that, then you can do research on the possible, say, beamforming solutions. Place an RAS there, do whatever you want, and see how the signal evolves. I will show more with our ray tracers. So we have a very similar ray tracer to Nokia's ray tracer. So also NVIDIA optics based, where we have these 3D environments. We also have downtown Oulu. So very handy tools if you want to just place a transmitter in the corridor and see, when you walk through the corridor, see what is the signal evolution throughout your walk path. And you can also add a little bit RAS there if you want. In this particular case, we have the RAS right there on the wall and transmitter right there. And so without the RAS, you lose quite a lot of the energy when you are in the shadows. But with the RAS, you can provide at least a little bit more. But also the ray tracers are really handy if you want to look at a little bit larger geographical areas and provide coverage maps and how the signal level is behaving over an area. So for instance, here's an example of the TX only transmission, and when we add RAS right there, there's a second RAS here, but it's not actually used in this particular example. And then study that, for instance, how the RAS improves the signal quality. There are quite a lot of these results will be included in the D1.3, so those will be public in the future. So to conclude this all, when we go to higher frequencies, we do need new channel models. And the main reason is, of course, that while the propagation does change a little bit, it is not really just the propagation, it is the joint operation of the hardware and your channels in whatever environment you take those. So that is it is now no longer that easy as in the lower frequency. It tends to be that you just take a relay trading channel, it tends to be correct. It takes quite a bit more at higher frequencies, But in the end of the day, the channels tend to be actually much simpler because they're sparse. So the main challenges actually are related to the panel estimation and so forth. But of course, the modeling, there's huge amount of work to be done. In ARIADNE, we have done huge amount of research on so many topics about the channels and reconfigurable channels and so forth. Unfortunately, we didn't answer quite all the questions in this project, so there's still plenty for the upcoming project to answer these for the channel characterization questions about in the different kind of scenarios and with different kind of hardware and so forth. And this has been really a joint undertaking of many work packages from 1 to 5. And the most exciting results are still to come when we really publish the D1 to 3, where we can really compare the models, compare the demonstrations to the theoretical models, and that is where we will also see, for instance, the ARIADNE long distance demonstration and how it compares against the link budgets calculated theoretically and so forth. So still a lot to come. So I will end here and thank you very much. And if you have any questions, I can try to answer.
Thank you very much, Joonas. Very timely presentation from the time you consumed, but also from the topic you presented. I think it's really true that lots of initiatives, projects are taking the metasurfaces and also the channel modeling in this frequency band as a, let's say, they are going, let's say, further from that what ARIADNE and maybe some other projects did. I don't see the questions now in the chat. I don't know, we have a time, so if somebody just unmute and have a good question for Joonas, it's the chance now. Okay, it doesn't seem to be the case. So thanks again, Joonas, for your very nice presentation. And I think the continuation of our presentations today fits very well, of course, to this what we just heard from Joonas, because you mentioned, of course, the channel modeling in respect to the usage or application of RIS of the metasurfaces. So our next presentation is actually more directly to the implementation of the RIS as such, characterization of such panels, let's say in this way, and also how they can be manufactured and then, of course, tested and demonstrated. So for this task, we had opportunity to work, or we still have opportunity to work in the ARIADNE project with Aalto University, with different people there. And today, Xuchen Wang, sorry for not pronouncing your name properly, will update us on, let's say, overall ARIADNE work in this respect and on the results we just, let's say, achieved, or we are just achieving towards project end. So, Xuchen, please go ahead. We cannot hear you yet. Maybe you have to unmute. Pooja, maybe you can also take a look.
Can you hear me now?
Oh, yes, very good.
Good. Okay. Sorry, I muted. Yeah.
No problem. There's always a magic button, you know.
Yeah.
Okay, go ahead.
Okay. So today, in representative of Sergei Tretyakov, I will present this work here, and this work was done by my colleague Sergei Kokkoniemi and also our Germany partner for the measuring the metasurface or RIS in the real environment, indoor measurement. Okay, let me start from the beginning. So what is our goal? Here, as you can see, our goal is to send a signal around a wall corner. So imagine you have a transmitter and also have a receiver. And this transmitter and the receiver, they are blocked by a wall or by any other barriers. And so in this case, the line of sight communication is blocked. So now we want to design an RIS or a metasurface that can beautifully redirect the signal from the transmitter to the receiver, no matter where the receiver is located. You can locate it at very sharp angle, like 70-degree, or very narrow angle, that like 0-degree. So no matter where the receiver is located, it can always receive the signal by this metasurface. So if the metasurface is properly designed, right? The frequency of interest, range of interest, we have in this project, we have 3 frequencies. One is 144, 144, and another is 157, and another is 170, around this value. I don't remember the exact number, but I will tell you later. Yeah. So now, so this is our task. We want to direct the signal by the metasurface to an arbitrary direction, and with a very high efficiency. And theoretically, it can be as high as 100%. So the first task is how we can estimate the required size of metasurface. So here you can see this structure. So there's a transmitting antenna, and this transmitting antenna illuminate a beam, terahertz beam, and then this beam is illuminated on the wall, and it is produce a specular reflection. And also, when the beam the beam excite current on the metasurface, and these currents will also generate anomalous direction radiation, and also it will also generate a specular direction radiation. So our metasurface, what the metasurface is doing is that it will generate the specular reflection that cancels the specular reflection generated by the wall. So finally, you can see the specular reflection disappear because of the presence of the metasurface. And also, it will generate a very strong anomalous beam in the anomalous direction. So it can be defined arbitrarily by the project need. So now the question is, how large is the metasurface we need in order to ensure the required field level at the receiver? For example, now we have this here. We want to we have this observation point. So how much the metasurface size we need? So we can calculate it using this simple formula. In this simple formula, the scattered field strength in the observation points is equal to is related to the power transmitted power PT and the gain of the transmitter antenna, and also it is related to the size of the metasurface, and also it is related to the designed reflection angle, anomalous reflection angle, theta I. So as you can see, if we require a specific value of scattered fields, and the transmitting antenna is fixed, so PT and GT is fixed, then we can uniquely solve what is the required size of metasurface. Yeah. So this is a simple estimation, and this works quite well. And you will see in the later slide that we estimated the size of metasurface as using this formula, and the project works very beautifully. So the next step is we have to design metasurface. Now, in this step, we assume the metasurface is infinitely large, and it is periodic. So in the design step, we assume metasurface is infinitely large, and it is periodic. And in this case, I show one unit cell of the metasurface. And the metasurface structure is you have a ground plane, and on top of the ground plane, you have a substrate like glass or silicon. Here in this project, we use glass. And on top of the glass, we have discrete impedance patches. And in this is one supercell, and then in one supercell, you see we divide the supercell as k subcells, and each subcell, the surface impedance, the material property is different, surface impedance is different. So we developed a very general theory that for an arbitrary set of surface impedance, K1, K2, K3 until Kk, and then you give incident wave direction and incident frequency, we can calculate all the scattered fields, including the propagating mode and also the surface modes. Of course, we only care about the propagating mode in the free space, but all the modes can be calculated by this method. And then we after calculating the we know all the material parameter, we can calculate all the scattering modes, but this is called a forward calculation. But in our Metasurface design, we really need inverse direction design. What is inverse design? In this inverse design, we know the incident beam direction and the frequency, and also we know the substrate parameter. What we want to know, what we don't know, is what is the surface impedance of the Metasurface, and what is the surface impedance of the Metasurface can generate our desired scattered modes. For example, we want to direct the incident beam fully to the anomalous direction n equal to +1 order of fluky modes. And in this case, we want to find what is the surface impedance. And this, because now forward calculation, I developed a theoretical approach, but inverse design, there's no analytical relation, a very simple analytical relation to do this job, inverse design job. So we use MATLAB optimization to optimize this surface impedance until our desired fluky modes becomes maximum. So this is a principle of design step. Now, according to this design step, and we design 3 anomalous reflectors, 3 RIS, and it works at 3 different frequencies. And the first one works at 144, and the second one works at 157 gigahertz, and the third one works at 170.9 gigahertz. And we, in our code, we set our objective that at this frequency, the anomalous direction signal should be maximum and 100% efficiency. So now, and then we optimize the surface impedance, and then we find the surface impedance for each design. And then, because surface impedance is only a theoretical model, in the final design, we must implement this surface impedance. So for each surface impedance, you see each supercell here. I have how many surface in 1, 2, 3, 4, 5, 6, 7, 8, 8 surface impedance. And each surface impedance can be implemented by the dog bone shape. And this dog bone, by properly tuning the structure of this dog bone shape, we can realize arbitrary surface impedance. So now we realize each sample one by one, the surface impedance, and you can see the shape, final shape is like this, and you can see the simulated efficiency. I mean, anomalous reflection efficiency. For lossless case, if I assume there's no loss in substrate and metal, and then you can see the efficiency is quite high. It's 99%, almost 100%. So it means that the beam from this incident direction fully goes to the anomalous direction, and there is very few power energy goes to the specular direction or other fluky channels. So this is theoretically this goal is satisfied. But when we consider the lossy case, for example, we consider the substrate is lossy and the metal is lossy, and this efficiency will be a bit degraded. But it is not avoidable because every structure is lossy. All the electromagnetic device is lossy, so we cannot overcome this problem. But the thing is here we kills all the parasitic reflections, and this is quite fancy because in the normal design approach, parasitic like reflect area approach or phased area approach, this parasitic reflection cannot be killed, cannot be overcome. So of course, now we use directed being from 0 degree to 50 degree, but we can also design using this general approach. We can design arbitrary direction, 70 degree and 80 degree. Yeah. And the next step is manufacturing. So the manufacturing is quite simple, and of course, it takes us a lot of time to figure out a simple way to manufacture this sample. And you can see we use a very standard photolithography approach, and we use glass substrate, and we because structure is like size is like micron, several micron. So we choose a photolithography approach, and we deposit the metal like a gold, and also deposit the ground plane. Okay, now this fabrication is finished, and then we now we get our sample. But before hand over to our Germany partner, we must ensure in our lab that our sample works really as we expected. So in our lab, we build a quasi-optical system, measurement system. And in this system, we use 3 parabolic mirrors. First, we have a Hall antenna signal that is the beam is divergent, and this divergent beam meet the first parabolic mirror, it will culminate it and like a parallel beam, and it will also focused by the second mirror, and it becomes a spot, beam spot, so that this beam spot is much smaller than the sample size. Then it is very easy for us to characterize and to extract the reflection coefficient or the anomalous reflection efficiency of the sample. And then you see in the end we put a mirror. So it's like the signal go to the sample, and anomalous reflection happens once, and then reflected back, and then happens the second time. So it's like a reflecting double time. So in the final S11, we must divide 2, like minus 3 dB, plus 3 dB. Yeah, because the power actually goes through the Metasurface twice. So we only need the one. When we calculate the efficiency, we must be very careful. The final results should be at the 3 dB. So this is the efficiency measured for 3 samples for 3 different frequencies, and you can see these all 3 samples, their efficiency is approximately 90%. That is expected in the simulation, and you can see all the parasitic reflections are suppressed. You see the specular reflection disappear, and also lateral reflection disappear. So only the anomalous direction have maximum power received. So now we finished our lab characterization. We hand over this sample to our Germany partner IAF, and we perform this indoor demonstration and measurement. And this is quite similar with our lab characterization, but without any quasi-optical system like mirrors. In this measurement, we don't use mirror. We mimic the real application scenario, and we you can see there's a transmitter antenna, and also the Metasurface is rotated 40 degree so that the incident angle is 50 degree. And then at the receiving antenna is rotated by a robot arm. from on top of the Metasurface, and it is in order to know all the scattering to all the directions. And you can see we measure 10-degree specular refraction and also minus 40-degree anomalous refraction. And you can see now the results. You see we test only one sample here, and this sample is designed at 144 gigahertz. And you can see for this sample, you can see minus 40-degree, you receive the maximum power. So in this picture is a gray solid curve. At minus 40-degree means that our incident beam is 50-degree, and it receives the maximum power. And also you can see the specular direction. Specular direction corresponds to the 10-degree. Yeah, 10-degree. You can see specular direction is quite suppressed. The energy level is minus 30 dB. So also we test other frequencies, but you can see because the sample is designed for 144 gigahertz. So when you're measuring other frequencies, so the sample doesn't work. So this is reasonable. But for the designed frequency, it works very well. And agrees with our theory, simulation, everything, and also our lab measurement agrees very well. So that's all. Thank you.
Thank you very much for a very nice presentation. And we have a question from Tang Fan. So Tang, you can just unmute and ask your question directly.
Yeah,
Okay.
thank you. Yeah, thank you for very interesting presentation, Wang.
Thank you.
And yeah, I have several questions. Very interesting design. First is you calculate how big the risk needed. So can you come back to your first slide? Yeah.
The size of Metasurface, right?
Yeah. So you have a eta 0 here. So what is the eta 0?
Eta 0 is the wave impedance of free space.
Okay, so 377.
Yeah, 377. Right, exactly. Yeah.
Okay.
Yeah.
Okay, yeah, very. So, I didn't really get the idea here. Okay, maybe I will read the paper to understand better.
Yeah.
So the second, my question is, could you go to you have a 3 prototype, 1, 2, 3 related to different. Can you go to? Yeah,
okay. Is 1, 2, 3 designed for 3 different refracted angles? No, it is designed for 3 different frequencies.
Yeah.
So
yeah. Okay.
So you see, the frequency is the first frequency is 144, the second frequency is 157, and the third frequency 170.
Okay.
So 3 different frequencies.
So if I understand properly, now you have a incident angle of 50 degree, right?
Yeah. Incident angle is 50 degree, right?
And what is your reflected angle?
Refracting angle is 0 degree. So this picture is like general picture. So in the real design, incident.
Okay. So
yeah, in the real design, we have incident angle like 50 degree from here, and when it meet Metasurface, it will directly it will direct the normal direction. Yeah.
Okay. Yeah.
So
okay. Yeah. So my question come to that how meaning that when we this kind of design is a quite narrow band, right?
You mean the performance is narrow band, right?
Yeah, because it works at one frequency and
it's not exactly at one frequency. You can see in this picture, actually we have some bandwidths, but not 100% bandwidth. Yeah, so you can see here from 140 it works. Yeah, and and 155. It also works depending on how you define your efficient bandwidth.
Okay.
If you require it is above 90 percentage efficiency, then it becomes narrow. And if you require 50 percentage efficiency is enough, then it's quite wide. Yeah.
Yes. Okay.
Mm.
So I
Yeah.
mean that normally in antenna we see
Mm.
that 3 dB bandwidth compared
Yeah.
to the big one. So do you did you have any information about the design about 3 dB bandwidth?
3 dB bandwidth means that it is half 50 percentage efficiency, right? So you can see in this picture, you can see it is works from 140 to almost 160 gigahertz, and this case works from quite wide range. And
Okay.
this works quite wide range. Yeah.
Okay. Okay.
Yeah.
Yes. Okay. So yeah. Sorry, I have many questions.
No problem. These are very good questions. Yeah.
Yeah. One more question from this measurement. I don't understand well. Like here you have M1 and
Yeah.
M2.
Yeah.
And here you do measurement to measure the efficiency of the meta surface of the risk you design.
Yeah.
So could you explain here how you can got the efficiency from this measurement? I didn't got this setup.
So the efficiency means that how when we assume that there's our incident power is 1, how much reflected power, how much power is reflected at the anomalous direction. For example, we have 0.9 power is reflected by the anomalous reflection. Then we define this efficiency is 90 percentage efficiency. So here in this system, actually, we are measuring how much power is reflected by the met surface in the anomalous direction.
So let me, if I understand this mechanism, so you from horn antenna, you radiated some signal to the meta surface.
Yeah,
and then it will be reflected to M3, right?
Yeah, it will reflected by the met surface first, and then it will reflected by the M3. Yeah, and then
okay, so you don't have anything to capture the energy at M3. So how you know the ratio between the reflected and reflected power and incident power to know your efficiency in this case?
We just measure S11. So you see the signal goes to from here, and then goes back, and received again. So we measure the S11. So actually, this signal go double times, twice from the met surface. That's why I say that we must be very careful when we compute the efficiency, because this signal suffer from the met surface twice, so we must add 3 dB at the final results. So the efficiency is measured by S11, reflection coefficient.
Okay, so meaning that okay, I understand it setup. Yes.
Yeah.
Okay, so last question go to the measurement. Sorry, too much question.
No problem. Yeah.
When you go to the last measurement here,
yeah.
You have a TX to the meta surface. So what is your dimension of your meta surface in this case? Total dimension.
Total dimension of my meta surface.
Yeah, diameter.
Diameter. As I remember, it is like 7 or 8 centimeter.
So 7 or 8 centimeter. Okay, can you come back?
You can see this. This is our test meta surface. It's very clear. Yeah.
Yeah, so I roughly calculate that with 7 or 8 parameter, meaning that the far field of the meta surface should be more than 2 meters.
Yes.
Can you come back to the measurement here? No, previous. Here, so you have a distance between TX and meta surface now only 70 centimeters. So meaning that the way go to meta surface is not plain way. So but in design, I think that you are designing the meta surface with plane wave. So why you set the distance is only 70 centimeter? How do you think? Is it still well, or we need to make it far?
This question I cannot answer you because this calculation is done by Sergei Kosonikov. Yeah, and I will forward this question to him, and then he will write to you in detail. Actually, yeah, you are right. Yeah, actually, you are right. But we have answer. I'm pretty sure. Yeah.
Yeah. Thank you. Yeah.
Yeah.
Yeah. Very nice presentation. So
Thank you
very much.
Thank you.
Thanks a lot. No, we are here not only to present, we are also to discuss. And there is also a question from Pooja, I think.
Okay. What is mean by periodic metasurface? This question. Okay. Periodic metasurface means that let me go to these slides. Means that all the how to say, so the unit cell is repeating in space. So it's like this is a super cell, and this super cell is repeating in the free in the space here, and infinitely goes to infinite. So this normally we model metasurface using periodic structure. This is for simple of mathematical calculation, and actually this is quite useful method. And in real fabrication, if your metasurface is enough large, like much larger than the wavelength, then this can be even your metasurface is finite structure, and then it can also be regarded as infinite periodic structure. So periodic means that all the supercell is repeating in free space, repeating on the surface.
Thank you.
Okay, thank you. So far, I can see there are no further questions. Thanks a lot again for very nice presentation, and
thank you
for the discussion. So we are now moving a little bit from, let's say, physical layer, but not completely. We are not leaving the physical layer completely, but we are going a little bit in the direction of machine learning, artificial intelligence. We apply these technologies in order to try to manage and characterize the networks we are working on. So this presentation will be given by Fotis Lazarakis from Demokritos and also Edwin Yaqub from RapidMiner. So they are going to share the presentation, and I think Fotis will start, if I'm not wrong. So Fotis, it's your turn. Maybe, I don't know, Dai has a question. I don't know if it's related to the previous presentation or if it's just stayed the hand raised. Sorry. Okay. I would say we are staying until end of the webinar. So if there are any further questions also to the presentation we just listened to, also or the first one, we can of course take it. But let's now listen to Fotis and his talk.
Okay. Okay, I hope you can see my screen. Khalid, is that okay?
Yes, very good.
Okay, thank you very much. Let me welcome you also to the last session of our webinar. As Khalid said, let's say the main presentation would be that of our colleague Edwin Yaqub from RapidMiner. But the goal of my presentation will be to give a short, if I manage that, very short overview of what we are doing in Ariadne with respect to applying machine learning and AI techniques for management of communications in the D-band. So some of the you have already understood from the previous presentations that we are focusing on the D-band, and very common characteristics at this, especially at these frequencies, are the directional links, the architecture for ultra dense networks, and very common blockage of line of sight links. So these are some of the characteristics that we then try to solve related problems by applying machine learning techniques with respect to mobility management, blockage avoidance, intelligent users association to access points, and radio resource management, and the list is not exclusive, I would say. So some research highlights. I would like to start from a figure, that figure taken from a paper that has been jointly authored by partners working at these topics in ARIADNE. This is, let's say, a review paper where there was an attempt to categorize problems in the broad sense, or topics that are commonly met in various systems, and so categorize specific problems at the sub-terahertz networks, and how they are connected to certain solutions that should be followed in terms of categorization of machine learning or AI algorithms that are suitable for this type of problems. So we can see a categorization from the physical layer up to the higher layers. So indeed, in ARIADNE, we have investigated a number of these topics, such as channel estimation, beamforming, blockage avoidance, user association, mobility management, and more. Just to get an idea. So the conclusion of all that work was that depending on the problem that you have to solve, then you have to use the suitable category, let's say, of algorithms from machine learning or AI. Just giving titles, let's say, of the topics that we have investigated in ARIADNE. One of those has to do with IQ imbalance at the terahertz wireless systems, where IQ imbalance at the transmitter and the receiver. So what we do is that we design intelligent transmitters and receivers employing machine learning techniques, and the focus is to these two blocks, a mapper and a demapper, which are trained so that they can map bits to symbols, and learning from the impairments of the systems and the failures, let's say, because of various reasons. Another one, and as you may mention, we are starting from the lower layers, and indeed we have investigated a range of problems from lower layers to higher layers, as I saw it at the previous slide. So another topic of interest is the beamforming optimization based on deep reinforcement learning. So it is the allocation practically of beamforming vectors to moving users using DRL. So this is the model or the framework that has been used using agents, single agent or multi-agent DRL, and this is the framework where we can see the neural network. We can see the main component, which is the modeling of the wireless environment, and then after the necessary training, we managed to have actions from the system to return actions, to get actions from the system, which is practically the selection of the beam, the optimum selection of the beam. Another problem that belongs to the lower layers is that we have done machine learning application for line of sight aware connectivity, where by means of either channel measurements real channel measurements or ray tracing data. And then we apply machine learning prediction so that we can predict line of sight and non-line of sight links in area, as we have already emphasized that from the very first presentation, that line of sight links are very, very important for the performance of the system in sub-terahertz frequencies. And moreover, this is why non-line of sight connectivity is very important through RISs in our project. So we go to another problem, that of the user association to access points. And here what we do is forecasting overloaded access points. So practically we have two different modules. One is one comes purely from the telecommunication side, where we simulate a D-band network, and we allocate somehow with the mainstream algorithm, we allocate users to access points. Then what we do is that we move to the second module that I mentioned, that comes from, belongs to the AI world, let's say. So what we do is that we use simulation data for training. We learn a K-order Markov model to predict how likely it is that a given access point will get overloaded in T time steps. So we can see here the two modules. One is written in MATLAB, and what we do is that we simulate the D-band network, and we allocate users to the access point with a conservative techniques. And here we have the second module where is based on an event forecasting engine. And then what we do is that we connect online these two modules using a Kafka interface. So what we can do is that we can dynamically get give and receive data between these two modules, and dynamically change our decisions. And moving to the last part is another perspective of the problem of user equipment association to access points in dense and evolving networks, where the environment also is a little bit different from the previous case that I mentioned with the forecasting. What we do is that we define the problem, and then we use a hybrid framework based on combining meta-heuristic optimization algorithms and machine learning models to solve the problem. At the first stage, and at the second stage to enable online optimization. But this last part belongs practically to the topic that will be presented by Edwin. So I think it is a good idea to go to Edwin's presentation. Thank you.
Okay, then I think we can proceed with the second part of the presentation from Edwin.
I think yes. I think that would be better.
For the time being, and then we can take the questions at the end.
Yeah, yeah, I think that would be better. Thanks.
Thank you for this very much.
Yeah, hello. Can you hear me?
Yes, Edwin, that's fine. Yes.
Okay, great. Thank you. So yeah, this presentation is about applying some AI ML methods for managing demanding high frequency communications. I must emphasize that this is just one of the many problems that the project solves in work package 4. So here we'll look at more data science perspective of how the low level details can be abstracted into a higher layer, and how we can solve some problems at mostly the application layer. So we see that the higher frequencies are of interest because we have the capability to deliver higher data rates. And if you just look at the pictorial, we have two users which are using the higher, let's say, frequency links with base stations, but these are also susceptible to the blockages. So we see that the user 1 is now connected with a separate base station because somebody just walked into the line of sight with the user, and that line of sight got interrupted or obstructed. So we see that the user association strategies then must also minimize these blockages. At the same time, we see that these future network systems are expected to deliver massive connectivity for wide range of applications and different resource levels required by the different applications. So one user may be happy with 10 Gbps at some point, and the other user might need more resources. So this leads us to a new definition of resource user association that must consider, of course, the backhaul capabilities of base stations and user requirements, but also minimizing the blockages before connectivity is established. And this would occur in a recurring fashion as these systems take shape and more blockages happen on the real time. So we need to take all these aspects into consideration. So then effective UE to AP association is then the main problem in directional line of site-based connectivity. And it is a joint, it's a joint problem of resource allocation, but also LOS blockage avoidance or minimization. And then we see, as Fotis just highlighted and earlier presenters, that future high frequency networks will be very dense and they will evolve. So then the solution, whatever it may be to establish connectivity, must also adapt in quick time span. The definition of the problem is that of an optimization problem. We have some constraints that we can use to explain this problem. UE is always only connected with one access point. And the second constraint is that, of course, an access point can host many UEs. And we have to minimize the overuse of resources at access points while also delivering what the APs assigned to it require in terms of bandwidth, for example, and at the same time, minimize the blockages. And the same constraints can then serve as the criteria to evaluate the optimization solution and the machine learning solutions or predictions quality. So when we were brainstorming around these lines, we figured out that in the absence of realistic or real world data and in the absence of test beds for future systems, we would need to simulate these scenarios, these network models. So a system model needed to be developed around which meta-heuristic optimizations were to be shaped. So we could simulate different network models, solving in the sense meaning to find the best associations. And with this data as serving us as the ground truth, we could train machine learning models. And if the model is having the predictive capability good enough, we could use it in a predictive component to replace optimizations altogether. From the technology side, then we, after some state-of-the-art analysis, decided to use technologies that are not just industrial strength, but also extensible. So Optaplanar for meta-heuristic and online solving, and RapidMiner for data preparation and machine learning. So we see that the hybrid framework brings then the two types of algorithms together, meta-heuristics, approximate random control, search optimization algorithms from Optaplanar. And so what we do is we generate a system model that comprises of UEs, user equipments. These are your mobile phones, access points, and their properties, of course, and their combinations. And then we needed to figure out what is a line of sight blockage. And so we feed this to the online solver, and we feed also the constraints. And then the solver gives us an assigned an attribute, which is the AP that needs to be assigned to a certain UE. We come up with a categorical label for each access point. And so now we can shape a classification problem. The model is trained on it. The model predicts the label. And at some point, we need to do some post-processing after the predictions to resolve the category of the access point back to a specific AP. Some implementation aspects. So we see that we have three major artifacts. We need to have a system model. And I have to say, we had to come up with a simplistic model. So we could experiment with the methods, how the AI and ML different methods could actually solve these problems. And also so we could make the dense and congested networks, which would have been difficult if we were to wait for the real data to be established. And then of course we use online solvers and machine learning and performance evaluation as pipelines. So these are some of the snapshots how we implement the system model and the other ML pipelines in RapidMiner. So just to give you a feeling, and this results in generating data sets. A data set then represents a network. This is one view of a network, and here you see just one access point, and the colored dots around it are mobile phones or UE. And what you see is that some UEs, when we cluster them with unsupervised learning, we can see that based on their location and distance from the access point, of course, some phases will overlap. So we identify, first of all, those UEs which may be overlapping in the line of sight of each other. And this is just for one AP. And we imagine hundreds of APs in future networks. So this is done to basically learn the blockages. Now coming to blockages, so initially we started with fully blocked line of sight links, and some domain experts in the project from Demokritos, they come up with the definition of identifying some links as blocked. This could happen, for example, if a network is some mobile phone users or UEs are behind some vegetation, buildings, or other obstacles. You cannot just assign them now the access point with whom the line of sight is blocked, but then the problem takes a different shape when we also think that a lot of interest is around partial line of sight blockages. So if you look at the cross section of this diagram showing a network, and we just focus on the UEX, the experts in the project, they come up with some blocking conditions that identify how many UEs would be blocking the line of sight of one particular UE for one access point. And we come up with all the blockers which partially block the line of sight of all UEs. And the stable snapshot shows us that what we come up with using the clustering approach. But that's very expensive to compute in real time. So we tried to train a machine learning model to predict these blockers. And we had good accuracy of approximately 80% with limited data set trained. And we keep this because this then model becomes part of our system model. But our main focus was to train a model which could predict the UE to AP association. So here you see a complex network where there are 600 plus UEs and 125 access points. And we want these assignments to be predictable. And so here in the zoom in view, you see that the access point 9 is located, and the lines that are incident on it are basically akin to line of sights, and the UE is on the other side, somewhere down here or here. And so they are connected to the access point. Now this connectivity must respect our resource requirement and blockage minimization constraints. And so this is just a view of the model that we were able to train. It's a gradient boosted tree model. And if you look at the individual trees, it's quite complex. So we see that it's not running onto some shortcuts in the sense of mapping inputs to output attributes. It's really looking at the pattern. We just had some intermediary results where we just trained a model to come up with a proof of concept if the pattern really exists in the data, that is the data found by the solvers. And we were not sure if the machine learning model would be able to figure out a pattern or if one exists even. So we just joined two data sets, and once we just trained on the minimal size of the training split using stratified sampling, usually is 80%, and you test on the rest of the 20%. We did here the opposite because we wanted not to overfit and also find the least subsetting of the data that would give us a very good accuracy. Now, obviously, this was a limited set test, but it does indicate that the pattern exists and the machine learning models can learn on top of meta heuristics. But if we change the meta heuristic algorithm, then the pattern breaks. That was another finding. So these are the results on top of a late acceptance algorithm learned into a GBT. So when we look at the ARIADNE way of modeling the network, there's an emphasis on mobility, because first the networks are dense, second they are evolving, and mobility and let's say the change in general in the network is very essential. So we identified there must be some triggers that we should be able to demonstrate, such as, for example, a network can be extended. If a new UE just appears anywhere randomly in a network, then certain UEs behind its phase or angle and behind the Euclidean distance from AP would now be blocked potentially. So now what we do is we figured out a control flow to execute the same RapidMiner processes which implement the system model, and we do it on the fly, and then we get the results back and we ingest it into the online solving, and then the solver gives us the next best associations. But that means we can do proactive handovers. If this work can be representing a real-world network, then these triggers help us to model changes in a living network and see how the technology performs in terms of qualitative and non-qualitative solution. Another trigger is to remove a UE. Of course, a UE can be shut off or crash. And so we again follow the same sequence of calls, and the system is able to identify, the system model identifies the UEs whose line of sight is now a bit released from one blocker. And so we insert it into the solving and the network updates itself. Similarly, we can tackle mobility that we just choose or the user chooses in the demonstration application a specific UE. And so when it is moved to another location, then for all access points, it's just showing one. We figure out the blockages that would be now affected for some UEs, and for those that are now released by one. Again, the same flow, and we also model an event to change the requirement. This is a fast-driven, we don't need system model for that. We can also then model access point addition. For example, imagine we need to drop a drone on a congested city area, or if there is a disaster situation, then the network has one more possibility to provide connectivity to the UEs. And so for this event in the demonstrator, we also invoke the system model, and we are able to provide one more option to connect to the solver. Solving never stops, and so similarly in the fly, we can also remove or crash access points, considering they're getting smaller and smaller in the future, and on every doorpost or around the lamppost. So some weather events or vandalism, etc., can damage access points. So this is also a fast to implement event. So in this whole approach, we are not just interested in the qualitative solution, but also in the non-qualitative, non-functional properties of the methods. What this helped us, this concept of triggers, it helps us to not just experiment with different trails of evolution patterns, but then also to save these changes in the network, which I just went over, and come up with a solution of which access points to assign when a certain change happens, and to save this data and convert it into training data, so the machine learning model, which is always hungry for data, gets better and better in its performance. So some of the key outcomes were, with which the PPT concludes, is the development of a hybrid solution. And we have a graphical user interface-based tool now, which behind the scene is using Octaplanner and RapidMiner. And so we can not just generate system models and load it and experiment with it, we can change the network on the fly. And also then we are now able to see how online solvers, how efficient they deliver the result, and if the model can be made more and more intelligent now that we know it has the ability to extract the pattern for the satisfaction of both constraints. So we have also paved the way for online learning, but that's not in the scope of the work. So in future, some of the aspects can be further enhanced. We know that the system model we consider is by design considered simplistic to basically experiment, as I said, with the methods. Now this can be extended now that we have closed the circuit on different levels. Also, the machine learning models can be further updated, and stretch goal is to change the definition of the problem altogether and have more realistic, more complex constraints in it. I would like to quickly show a small video clip, and I'll just skip over some of these steps so you get a feeling, if I may, about what this demonstrator looks like and how you can actually see it in action in real time. So I'll just enter my full screen and let the video play and provide short hints. So this is the final interface. You see some panels where the interface will render its visualization when we load the data. And these are the data sets. So here you see a network plot. First of all, you see an online optimizer and an online predictor tab. See a network plot, and what you see on the right-hand side is the solution panel, where you see that the problem state space is really large in this network. These are the possible combinations of UEs assigned to APs. We also see that the score of the optimization is shown here. Then we see how many access points are there in the network and how many are used by the system once we start solving, and the resource required and the resource available. We also have here the triggers that we just went over. And so we can also drill deeper into the assignments. So this is a tool basically designed for telco engineers, and of course some plots to help us view the optimization progress of different algorithms and the of course the quality of the solution. So now when we go ahead and just solve the problem, we see how quickly the associations can be rendered. So it takes a few seconds, and as you see, the numbers are being improved. That means that the blockages are minimized, and the assignments you see in the network plot it updates very fast. The optimization progress is also very fast, and pretty soon we find all the assignments that we want. I'll forward a little bit to show you some triggers. So we want to add a UE here. We add the X and Y location and the bandwidth we require. It takes a bit time, so I show you a little bit here in the background. We invoke these RapidMiner processes, which basically are visual pipelines according to the recommended specification by ITUT. But we also are basically interested in executing it programmatically. So you can do that. And we like to avoid going over the network to any web services, because in optimization, we try to do things as fast as possible. So here we added just a new UE. So the network is now changed. And we can also see that the first executions take a bit longer, but the second executions take just a few seconds. So now we have a second UE added to the network. And as soon as we add it, the system is able to nearly instantly, in millisecond ranges, I believe even microsecond, assign it to the best AP. And so we can also move UEs. We can select the location and just fast forward a little bit to save time. And we have moved the UE to this location. You can also see all the UEs in the list boxes, so you can move them further. And at some point, we're trying to extend the network in a certain direction, but we can also add an access point in a certain direction. Imagine a drone scenario. So it does not mean that when the network updates that if there is an additional access point that it will eventually be used even. But at some point the algorithms decide, and we can move more and create more changes. And now you see that the new access point is also being used. So I just fast forward to a little bit of a stress test. We continue to remove certain access points, make the problem size smaller but harder. So we have less and less options to allocate the UEs. So you see we start removing access points, and with the online solving, we can really show a lot of these triggers in a very visual way, and also save in the end all these changes with the ground truth data found by the solver. So if we keep on removing, at some point we are out of resources and hard constraints cannot be satisfied. So you see the combinations are found more and more, but each of these combinations is a complete solution. So what this work helps us do is that we can get a point-in-time solution for associations in dense networks which are experiencing change. And you see at some point we are run out of resources, but as soon as we add more access points, the whole network is continuously in millisecond, microsecond ranges able to improve its associations. And you see the results in other plots as well. So I will just fast forward to the machine learning part to save some time. We have, let's say, now saved these. We have to save these results. We can drill down the plots and learn more. And here we go. We are in the machine learning tab now. We have trained 2 models, gradient boosted tree-based models, and we load the problem instance. And then we can we can save the solutions, and we can click the predict associations button to get predictions from the model. And you will see it takes also around 1 minute, but it needs to prepare a lot of data. It does scoring, which means application of machine learning model. So a process is called from the background, and predictions are obtained for 82,000 plus points. And this is the shape of the network after the associations are predicted. Now you see the network plot is a little bit skewed on the southwest side, and some APs are overloaded, and there are also a lot of blockages that machine learning predicted, which were not as good as in the online optimizer. This is because the model is not really trained on a lot of data, but now with the help of this online optimizer tab, we can save as much data as we want, as you see in the left panel. So if we see that with just a few data sets, the model was able to still respect the constraints to minimize blockages for most of the links, that shows that the pattern is being learned. And so we can also see if we apply the stronger model, then these blockages are further minimized, and the resource overloads are also further improved. And the shape of the network plot also changes in just a few seconds. So here you see the results, and you see that the network plot also looks more balanced. And what is also interesting is the scoring time of these machine learning approaches. So when we do the prediction, we need a little bit more time, because there are 82,760 points here. But after the prediction is resolved to an access point, for a single UE, we are around 47 millisecond ranges, which is fast, but it could even be faster if we have a simpler model, like, let's say, performing at the same capacity as a gradient boosted tree. So after retraining, we hope that the model's predictive quality and strength and stability improves further. So with that, I stop the demonstration video, and thank you for your time and attention.
Thank you very much, Edwin, and also Fotis. So far I don't see any questions in the chat. I don't know if somebody has an immediate question. Just unmute and ask. Okay, I think it was really interesting to see actually what did we achieve by using the AI in general in our project. And we know also that there are lots of projects around today applying these technologies in order to try to improve different things, also network management and even the network characterization and so on. I think it was really good overview of that, or part of this what we did in our work in the ARIADNE project. If there are no further questions, I would ask our advisory board members maybe to provide a sort of feedback if they feel like this, of course. Just to, let's say, provide their recognized expert view on some of the points we just presented. And maybe I would start from Professor Tadao Nagatsuma. If you can, let's say, provide feedback if you think it's reasonable on the presentation and ARIADNE project in general.
Okay, I'll say a few words. First of all, congratulations on completing ARIADNE project with a great success. This project aimed at the use of the D-band, which is the most promising terahertz band deployed first in the marketplace of the beyond 5G, because of the availability of advanced front-end transceiver technologies enabled by silicon LSIs, as well as compound semiconductor-based LSIs. This project has made many challenges for channeling modeling, characterization, developing practical metasurfaces or RIS, and the application of machine learning in the management of terahertz link. I believe these outcomes achieved in ARIADNE project will promise the future of terahertz communications, and I hope that the colleagues involved in the project continue enhancing the research in more worldwide scale. Thank you very much for inviting me to such a fantastic webinar. Thank you.
Okay, thank you very much, Tadao. And also from our side, it was, or it is still, because we have to clarify that ARIADNE project is still running until July. We had to extend a little bit because some of the, let's say, components we needed for the demonstrators, we couldn't get through because of known problems, COVID and logistic in general. But yes, you are right. We concluded, let's say, the 99% of our research work, and now working towards demonstrators to implement them. And thanks a lot for supporting us with your advices during the project lifetime.
You're very welcome. Thank you.
Then I would ask also Professor John Vardaxoglou to provide his feedback.
Okay. Can you? All right.
Yes,
you
yes,
can hear me. You can see me.
Oh yeah, oh yeah. Nice to see you.
Nice to see you too. Yeah. Yeah. I think my view is that you've done an excellent job in, from what I see, the 3 presentations. And because I've only been part in this meeting, so I don't know all the nitty-gritty details, but it appears that they've done quite a lot of work quite successfully. I mean, my expertise is in metasurfaces, and I know Professor Tretiakov's work, so I know he's excellent, so I'm not going to comment any more on that. Just a couple of things on an advice. I know he's not finished the project. Professor Alexiou mentioned Beyond Shannon in the beginning, and that kind of stuck in my mind. So in your conclusion, you may want to bring all these different elements together as much as you can, because I know it's impossible to have a demonstrator with everything in, but someone would like to see the project in a holistic view. And how much beyond Shannon have you achieved? I know terahertz is the next big thing in communications, and I'm sure you've done an excellent job in individual elements of the project, but someone would like to see some conclusion, and not, perhaps maybe today wasn't the right forum for that, but as you're coming to the culmination of the project, you might want to think to bring that, and also in advertising, as promoting the thing. It's just to someone who is not a super expert in the area. And if you want to get further funding, that would help. Yeah, and I think, it's not an easy area. I mean, you had a lot of challenges at the beginning, and you have done quite a lot of successful work. So I congratulate the team. I know how difficult it is to organize it, and to bring the teams together. But yeah, that was my advice. I'm an advisory board, so I give you an advice.
Thanks a lot. Thanks a lot. I mean, yes, it's not that easy also to present, let's say, the ARIADNE results as a package. We know it because we tried several times. There are some, let's say, high-level publications like the newsletters where we are trying to present it to, let's say, a bit wider audience. But I confirm it's not easy, but we have to do it anyway in the scope of the project. And I think now having the demonstrators, for example, what we are planning is to present a simple RIS demonstrator at EUCNC. It's one of the major, let's say, conferences, at least in Europe, where the projects, European projects mainly around the networking or networks and so on, are present. And I think having this let's say, material and real hardware, I think we will be also able really to create good publications to present this work from a level to be understandable to others, including the framework beyond Shannon. I mean, we have it, but of course, let's say behind the framework beyond Shannon, it's lots of maths, it's a lot of modeling, characterization, and this is really tough. But yeah, thanks a lot, and I think this is something we have to keep in mind in our, let's say, future activities, especially in our, let's say, dissemination part of our activities.
Okay, good. Thanks.
Thank you. And then last but not least, of course, Patrick Gallinari from Loughborough University. If you can provide your feedback.
Yes. You hear me?
Yes.
So I want to thank you for the invitation to this very nice project. Well, I'm not an expert in wireless communication, but I can at least appreciate what you did with statistics and machine learning. Also, for me, you have been working on a very large variety of problems, like involving control, forecasting, classification, and last you mentioned online learning. Well, I guess that are all very difficult problems in this for this kind of setting, of practical setting. And also, you have been able to deploy several different types of AI or machine learning techniques corresponding to each of these problems. So okay. So I really appreciate what you did. I repeat that I think that all those problems are extremely complex. Okay, and simple application of machine learning techniques is not enough, and you have to develop a lot of know-how and a lot of expertise for these different problems. And then there is this problem of okay, my machine learning requires data, so like Edwin described, there is no yet existing infrastructures that exist and that could provide real data. So, I think you manage well in developing your own simulators and performing tests on these different data sets. Okay. So maybe I have a question regarding this way of proceeding. Questions about how close are maybe your simulations to what you envision real data sets or real future real settings, and do you consider that you will be able to test on something that is close to the real settings? So that's my question.
So I think this is a good question for Edwin, maybe also Fotis. How realistic can you, let's say, represent the networks? That is, let's say, simplified summary of your question, I would say, by using the machine learning and AI.
So I can maybe say a few words. It is hard to answer this question because we see also from other work packages on the lower layers, the level of complexity these systems actually entail. What they carry is really complex. For example, what we see in the physical layer and in the introduction of RAS, which we did not even tackle at the application layer because we had run out of resource bandwidth. But these problems would need to be continuously extended. So what we have done is a baseline, I would imagine, that can be extended and with more. So this one of the future directions is to make the system model more complicated and sophisticated so it represents more realism. And then also to continue to add the constraints that are in real time. And finally, also, for example, we do not tackle the time, space, and frequency domains as the real networks must. We tackle space to some degree, we tackle time at the non-qualitative level, but these spectrums that are allocated, these are really more scheduling problems, a subset of resource allocation than pure resource allocation. So we try to basically build up a vantage point by understanding these three pillars: system model, solving requirements and adaptations in real time, and then see if machine learning can even detect patterns. So it's not that close, I would say, but I think with the vantage point where we are standing, we do see a very great promise these methods contain. But I also see that there are maybe other approaches that the other partners applied, which could also be explored further. But even with the meta-heuristic and machine learning combination, the state of the art has not really explored them deep enough, especially for online optimizations and online learning. So the promise is there, but I think we are still a few steps away from the final deployment ready requirements. So that would take some time and more investigations. But I must say that Fotis may have a few more words to add.
Okay, no, no, I don't have many things to say more, because I think that Edwin covered 100% the topic, and what I would like also to say that we start the first step is to define the telecommunication problem, and when we simulate a network, then this is the starting point, and then machine learning or AI comes to solve a specific problem. So I think this is what Edwin said previously, that we started from some simple cases, some baseline, and we then in the course of the project, we started to do more complicated models. So the representation of the system itself at the telecommunication side, where I come from, we cannot say that are very close to to a system that will be developed, let's say, and we will have these characteristics. But we are investigating step by step that indeed we have very good results when we apply machine learning or AI, depending on the problem of the category of the problem, and we keep on doing more complicated things. So I agree with Edwin that maybe at that part, at this point, we are not very close to very realistic solutions, or something that looks very close to what will be a real system. But we have gained very good knowledge, very good knowledge from that, and we keep on doing things that move closer to the reality.
Okay.
Thank you, Fotis. Yeah, I mean, the data sets, as you mentioned, Patrick, I mean, some 25 years ago, when I was young and a PhD student, so we had, I did lots of simulations, and then at conferences and presentations, then very frequently I received the question, how realistic are your traffic models? Or, and this is, how realistic is the data we have and so on. At this time, it was probably no go to get some data for the research from, big telco operators and so on. But I think with the application of the AI and machine learning, I think we are getting there, because it is really, let's say, a huge need to have appropriate so-called public data sets. And I think also the 5G PPP community in the corresponding white paper, where Ariadne actually provided the editor, let's say, elaborating on different aspects of application of AI in telecommunications and future networks. One of the, let's say, main conclusion, and also some proposals how to deal with this, is actually on the public or accessible data set, which can be then used by wide research and also industry community in order to let's say, be able to simulate, let's say, in this way, the networks as realistic as possible. So I think maybe this, let's say, attitude is now changing, and I think that the community is getting closer to this type of open data sets for further investigation. Let's hope on this. Okay, I'm just looking into the watch, so we are already a little bit after the planned duration of the webinar. Nevertheless, I don't want to let's say, escape to give a chance for a last question. I don't see any in the chat. Okay, it doesn't seem to be the case. So I would then first, of course, thank to the our advisory board members for, let's say, following up what we are doing and also joining us at the advisory board meetings like this one. Thanks a lot. Thank you very much for all participants, particularly those on outside of Ariadne project, and many thanks to the presenters who took, of course, some time to prepare those very nice presentations. I think, I have a feeling the presentations were well received. I don't know, Angela, if you would like to, let's say, give a last word on some expectation and maybe provide some general answers to all what we discussed today. And I think with this, we can also conclude the webinar today.
Yeah, I think just on the feedback about the Beyond Shannon idea by Professor Vardaxoglou, I think this is definitely what was the objective here. We try to approach this objective from various angles, and what you will see in our demos covers partly this attempt, let's say, to introduce tunability and programmability by means of RISs and machine learning. So some aspects of this Beyond Shannon are materialized in our studies and in our demos. And I think I would close this webinar by inviting people to our website for the latest news on publications and activities, and also to our booth at the EUCNC, where we expect to be able to show some of these things. Everyone is mostly welcome to come and see. So over to you, Khalid.
Okay, thanks. Yes, and this is true. There is much more to learn from Ariadne, or just at least to listen from Ariadne that we provided today. It's only a part of that what we did. So please visit our website, contact us. If you are around EUCNC, will be a good opportunity, of course, also to see something. And with this, I would say, let's close the webinar for today. And again, thank you very much for your participation, and see you next time. Bye-bye.